Good morning. I welcome you all for this lecture, and today's lecture that we are going to learn an important topic titled steady state gains. So steady state gains are the values of function that are useful for comparing vehicle handling capabilities. So we can consider vehicle to be a control system model. So if you look at, we have expressed the fundamental governing equation of our bicycle model for pure cornering through equation sets called the state space equation sets. So we know what is the state matrix, and that involve on the vehicle parameters, and state matrix are very useful to find out the responses of state variable and so on in generic way to say. So if that is so, there are two degrees of freedom bicycle model where in our study we have not importantly considered suspension into account. The model has become 2-degree freedom model involving only two responses of your vehicle primarily. What are those? One is lateral velocity response, another one is yaw velocity response. So these responses are because of there are inputs to the vehicle. What are the inputs to the vehicle? The input can be the steering input by the driver whenever there are required maneuvering to be done in the due course of travel on the path. Or it can be also environmental inputs, like you can have wind gust is acting on your vehicle when you go on a straight path. So because of that, there is a blow of wind in lateral direction. You would have to develop necessary lateral force at the tire road interaction. So that is also another input that we could say that you will have to, your vehicle have to give these type of responses. Right? Why this we are looking at it is because the vehicle can be looked at as a control system model. So as we have understood clearly, the main objective of our lateral dynamics is to study two aspects. One is the directional control, another one is vehicle directional stability. So these two aspects can be well understood and expressed through mathematical equation with a simple bicycle model is what we have understood, learned, and we are learning in that. So in that connection, in the last class, we have looked at what are called transfer functions of your vehicle for your handling dynamics. So transfer functions essentially gives you for a given input, what is the output. If you know, you can find out. So it is basically the ratio of output by input in a Laplace domain is what is referring to transfer function. So how can we get this transfer function for our bicycle model? There are two transfer functions. One is lateral velocity transfer function, another one is yaw velocity transfer function. How can we get that is what in the last class we have learned. So what we were doing, we were able to represent your state equation into an algebraic form, algebraic equation, and then with an application of Cramer rule, we are able to get your transfer function is what in the last class you have learned. And I'm going to continue with that particular transfer functions with this today's class to understand what are called steady state gain. So the steady state gains are quite useful vehicle characterization whenever you want to represent your vehicle as a control system model. So if you say control system model, there would be an input and your vehicle characterization would be defined by this steady state gain or your transfer function, and then you will have some output. And that output can be looked at, is that the right output that we get? What do you mean by right output in a case of a bicycle model? If my vehicle is responding to my input given steering angle during a cornering maneuver, and it is going along the path, that means that output is correct. If that is not so, then I have to give the feedback. I have to take the output feedback. Again, there would be a feedback control function, and that would go and correct the error involved. So that is essentially can be an open loop control system model or closed loop control system models to best describe the dynamics of any system. And with the help of control system model, we can have our precision outputs, and that precision outputs for handling or the directional control and stability of your vehicle. So this could be achieved. So when you look at as a control system model your vehicle, these steady state gains are an important parameters, and those parameters are quite useful parameters to do a comparison of vehicle handling capability. So that is what we are going to see in today's class. For that, I am going to share my board. Let me share my board. So you're able to see this on the screen, and this is essentially what we were doing in the last class. I'm just going to go through with that and a small correction in that what we were doing in the last class. So in the last class, we were just taking these two equations describing our pure cornering governing equation, and we were able to reduce that into an algebraic form. That's what is called its characteristic polynomial. And finally, we are able to apply Cramer rule, and we are able to get these transfer functions. So what are the two transfer functions? One is this function, which is lateral velocity transfer function. Another one is yaw velocity transfer function. So how do you get these transfer function? Is by the application of Cramer rule. So to apply the Cramer rule, what is needed is representation of your governing equation, this equation, to be represented in an algebraic form. For that, I just substitute this trial solution. When you substitute this trial solution, you see there are two simultaneous equation of two state variables, and then those become two algebraic equation. C times x equals b, where this two simultaneous equations of variables v and r. So if I can represent these values of v and r by applying Cramer rule from linear algebra concept. So that's what is essentially to represent one of the variable lateral velocity, replace the first column by your forcing column from B vector, and then have as it is your C, second column of C matrix, and find the determinant. So this variable value can be represented as ratios of two determinants. So numerator determinant is obtained by replacing the first column by B vector, and dividing that by determinant of characteristic polynomial. So determinant of C matrix. So what is the determinant of C matrix? That would result in a characteristic polynomial. So you would have here a polynomial in denominator. Similarly, this determinant also will result in a polynomial. So basically, your transfer function of this lateral velocity for the given steering input is represented as ratios of two polynomial, and those two polynomial is what yesterday we were trying to get. And in that process, I just have to explain you here, we made small correction. We have to do it now, and that correction, anybody has gone through and found that correction required? So when I multiply these terms here, when I multiply these terms here, that is these two terms, right? When I multiply these two terms, I have this mu into this is what are the last two terms. So here this mu into first term when I multiply, it is m a c alpha f by u into u. So u goes off, and that I have forgotten here. So there is no u in the denominator. There is no u here in this denominator. Otherwise, rest all correct. So your equation here, you will not have u here, and this would be u square as it is, whatever that. So u squared by L squared C alpha f is what would be multiplying this factor when I take this out, and I would have here, this is with u square. So 1 plus k3 u square would be there, where this k3 is what is called the stability factor. We will see that when we look at our stability analysis of your vehicle. So if you have understood this and got your denominator polynomial in a Cramer rule, is this, which is the quadratic equation function of s, and you have these coefficients obtained from vehicle parameters nicely. So this ratio is what is going to give me now my transfer function of lateral velocity for the given steering input. And this ratio would give me this. So I asked you to work out this, and these are the results. And these are called the transfer functions. So now the transfer functions are always represented in Laplace domain in control system design, right? So where the variable is s, and that s can be replaced by j omega to get what you call the frequency response function, that is called the FRFs uh, in frequency domain. So this is something that we will look at in more detail later on. There are many experiments that are performed to find this frequency response function. So you could see this, its Laplace domain is some complex domain, and this is frequency domain. Similarly, you can also representation of your transfer function in time domain. That is what is called impulse response function. Impulse response function. How do you get that impulse response function? If I excite any structure by a pulse, whatever the response that I get, that is what is an impulse response function. So how do I get the impulse response function in my bicycle model? When I drive my vehicle, I give steer pulse. So I go straight and I give pulse, and pulse means I just give some steering angles and immediately take it back, the shortest duration. That's what is the kind of pulse that you can give. When you give that and you get your response, that's what is called impulse response function. And that Laplace transform is what is called transfer function, or its Fourier transform, what is called the frequency response function, and so on in mathematics. So keep that aside. And then what is steady state gain is what today we are going to learn. So for that, I'll have to take my transfer function, and then in that I have this yes, that I have to make into 0. Why? Because steady state response of any system would attain at t tends to infinity. At t tends to infinity, right? So that is what is that. So in there is a theorem called final value theorem. So as t tends to infinity in Laplace transform, or in Laplace domain, that is equivalent to s tends to 0. So when I make in my transfer function s tends to 0, what do I get is what is called the steady state gain. So I'm going to get that steady state gain and then look at its physical insights to represent the vehicle handling characteristics. Right. So today's lecture is lecture number 24, and today it is 11/10/2021. And the lecture topic is steady state gains. So there are three important steady state gains, and that are very important. So one is yaw velocity gain. Yaw velocity gain. Another one we are going to look at today's class is lateral acceleration gain. Let me ask, what happened to lateral velocity gain? So instead of lateral velocity, lateral acceleration has always been an important parameter for vehicle handling aspect. Of course, you get your lateral velocity gain when you substitute s tends to 0 in its transfer function. But for a physical insight, we'll look at lateral acceleration gain in today's class. And then the third one is curvature gain. So how are these steady state gains are obtained is what is our starting point of today's lecture. And then let us look at how are these gains are going to vary as function of vehicle speed is what is that we are going to discuss. So what is your yaw velocity gain? It is r by delta as s tends to 0 in the transfer function. And I would say that the capital letter, yeah. So what does this capital S, yeah, refer to? Yaw velocity gain. So the notation for that, yes, yeah, you see in otherwise in some textbook, capital G is what is used. Yeah. So this is what is the notation in the textbook. You'd see Wong. And yes, capital letter S is what is used. You would see that is in JASA textbook. So this books to book, it varies, but doesn't matter. So this is S tends to 0, that would give you your answer. So what was our R by delta that we had in the last class? Let us take that equation and then we'll substitute in that this. So I have this. So MA C alpha F into S, right? MA C alpha F into S plus L C alpha F C alpha R by U, L C alpha F C alpha R by U divided by S squared plus S plus, here I had this term, which is delta, that's L squared C alpha F C alpha R by U squared into K3 U squared. This is right. That's what I was telling you to correct it here. So if we do so, it's going to be L squared C alpha F C alpha R by U square into what was that equation? 1 plus K3 into U square, right? K3 U square. So this is that you get. So in this, if I substitute S tends to 0, this term is going to be 0. These two terms are going to be 0. I would have my steady state gain now. It's going to be L C alpha F C alpha R by U divided by L squared C alpha F C alpha R by U square into 1 plus K3 U square. So now, so this U and this U square, U becomes and this L and this becomes L. What would be the change now? C alpha F, C alpha F, this goes up. So I have now U by L into 1 plus K3 U square is what I have, correct? So this is what is called a steady state gain. G, velocity gain is given by this. So let me use, so let's call this as equation number 1 for steady state gain topic. So here you see what is U is forward speed, L is your wheel base, and what is K3 here is stability factor. So what is K3? So K3 here is called the stability factor, and that's given by M into BC alpha F minus AC alpha R by L squared C alpha F into C alpha R. So I can rewrite this as this. So this mass I want to replace by total weight of the vehicle. So it's W into BC alpha F minus AC alpha R divided by G into, because I have here W, so divide by G, so that become mass, L squared C alpha F C alpha R. So if I take this individual term, divide by that, what do I get? WB by GL square, and C alpha goes off, so I will have here C alpha R remaining minus W A by GL square into C alpha F, right? So now you may look at here an interesting thing. So I will take this L squared as L into L. So WB by L is nothing but we know that WF, the load in the front axle, is WB by L. Load in the rear axle is WA by L. Yeah.
So in the first term, WB upon GL square C alpha R will be there, right?
Where here?
Yeah, in the left side of the negative sign and down.
Here.
C alpha R should be there in the denominator, right? Here, left of the
Yeah,
screen.
so this see, I just divide this B C alpha F by this. So C alpha F, C alpha F goes. So this is R.
Yeah, okay, that's what. Oh,
This is R. And this is F. Well, this is F. Is that clear?
yes, it
This
is.
C alpha F, this goes, and there is only one this term,
Yeah.
and this and this.
Yes.
And you know, these two are from taking a vehicle. This is my vehicle on the road surface, and this vehicle, normal loads, WF and WR be represented by, if this is my CG location, this is A and this is B, and total length is L, wheelbase. I can represent this by simply taking moment. So if this is W, so I would be able to express WF as WB by L and WR by WA by L simply by taking moment about this point. I will have first one, taking moment about front axle interaction with the road, I'll get this. So this is well known in a simple free body diagram in a static condition, and what would be this. And the same load distribution would be there in our bicycle model. Is why? Because steady state motion. So when you consider steady state motion, there is no load transfer. There is no suspension bicycle model consider. There is no load transfer. There is no load transfer. This WF and WR are constants. So that is what is now here. I will have WB by L is what is going to be WF by G into L now into C alpha R minus here WA by L would be WR by G into L into C alpha F. Am I right? BC alpha R. 1 minute. There's some small mistake. Yeah, you are saying that only, right? What is the mistake here is when I was writing this stability factor, I just have made a mistake. BC alpha R into AC alpha F. Please do correct it. BC alpha R into AC alpha F. So this is going to be then F, and this is going to be R. I'm just writing it with the red one so that it is corrected. So this is going to be F, this is going to be R. So please do this correction because I just have written here a mistake, right? What is stability factor? You have done it in the last class and we have written that is BM into BC alpha R minus AC alpha F within bracket divided by L square into C alpha F and C alpha R. So why do I write this all? You would get immediately now is all because this can be nicely reduced now 1 by 2, sorry, GL if I take it out. What is that? I'm having it here WF by C alpha F minus WR by C alpha R. So you would immediately say that's nothing but KUS, which you have seen in the steady state motion. So that's KUS, understeer coefficient divided by GL. So this is what is on this side K3. So you may wonder what is the relationship between K3 and KUS. So that gives you here. Please make a note of it. There are textbook when you look at the same model when you take it for stability analysis. K3 is what is pronounced for the discussion. When it is for response study, then KUS will be pronounced. But it is related. So K3 and KUS is related by this. Right, so this you should remember. So if that is so, then I can rewrite my understeer, rewrite my yaw velocity gain, which is steady state gain, as this way. So it was R by delta S tends to 0. That's going to be U by L into 1 plus K3 U square. You have written that can also be rewritten as this way. How we can also rewrite that in this way. So that's going to be U by here. I have L taken out. I just take it inside. So L plus. So when I take it inside, so K3 if I substitute LL goes off, it is going to be KUS by G, KUS by G into U square, into U square. So this is forward velocity small u and this. So you can see this in some textbook, and you can also see U by L plus KUS by G into U square, right? So you can have this. So what is the unit of this? The unit of this is yaw velocity. It is sort of rotational. When you see from top, the orientation of your vehicle changes is what is witnessed by yaw velocity. So you would have that would be given by radians per second and divided by steering angle. That's what is in radians. So your unit of this is unit of steady state gain, that is yaw velocity gain, is given by radians per second per radians, right? That's what you should understand. So this is what is the expression for yaw velocity gain. So now what is that advantage of looking at yaw velocity gain? So by having this yaw velocity gain for a different steering input, what would be the orientation change of your vehicle can be witnessed with this steady state gain. So if you have a different vehicle and their K3 or KES will be different, and when you have the vehicle parameter L might be different. So with respect to that, for every vehicle, you would have this steady state gain, and you would be able to look at this gain variation as function of speed. So that's what I'm going to plot now. So if I plot that, let me take it on y-axis, this gain, yaw velocity gain, it's given by radians per second by radians. And on the horizontal axis, let me take forward speed. That's in kilometers per hour I'm taking. So if that is so let us have this 0, this is 50 kilometers per hour, this is 100 kilometers per hour, 150 kilometers per hour, and so on horizontal axis. And here I have this maybe with the numbers. It is going to be some value, right? So I do not have here the realistic value. So you may take as per this data here, there's 10, 20, whether it's degrees per second per degree. So you can also represent degrees per second per degrees. So there's something 10 and 20 values. These are some realistic value because you take some vehicle data with wheelbase L equals 3 meters vehicle. It's a long vehicle. And then your turning radius, say 30 meters and so on. So there is some given vehicle parameter. For that, if you calculate your KUS is comes out to be 0.0175. What is this? The unit of KUS in radians. It is in radians. And you can have the same vehicle. This is for an understeered tendency of the vehicle. Oversteered tendency of the vehicle, KUS would be, its negative value. That value for the example vehicle is 0.035 radians, right? So you can take this. So if that is so, you will say that if that vehicle has to behave as a neutral steered vehicle, KUS should be equal to 0. So when I put in this KUS is 0, I would have here my variation of yaw velocity gain is given by U by L. When U is constant in steady state motion, L is constant, I will have my variation of gain as function of speed would be changing. So forward speed constant means I'll have one, but next I'm varying the speed. Varying the speed means I'm not accelerating. That's very important. In a steady state motion, I'm not accelerating. I'm going to give some steering input like no, you are going to look at for the chosen speed at that time what is the value. So you will keep plotting it, and the variation would be now linear variation. That's what you would see. So the variation would be linear. So I'll have some speed and then accordingly my data would change. So this would be what is neutral steer tendency of my vehicle. When this would happen when KUS equals 0. So in this KUS is 0, I have my gain is given by U by L. So I take U here, U0, 0. u 1 kilometers per hour is 10, like that. If I increase 10, 20, 30, 40, I will have accordingly these values, and the variation is linear variation if the vehicle happens to be neutral steered vehicle. If a vehicle is an understeer vehicle, for the chosen vehicle, our understeer coefficient is 0.0175 radians. If I substitute here, what would happen as I increase my u, this would be keep increasing. When denominator, this KES is taken by this value, so u would be increasing in a square value. So my denominator would keep increasing as u also in numerator increases. So initially, for some time, I would have my increase in this value gain, and then it would attain some value maximum, and then it will be dropping. So there is a slope where you have slope 0, and then you would have some corresponding speed, and that speed is what we call it as the u characteristic speeds. You remember. So u characteristic speed is one. This would happen when the delta f required is equal to 2L by R. That's what we have seen in steady state motion. So when it is 2L by R, you see whatever the speed corresponding is what is this. And we have got it how? You have to recollect this fundamental equation of steady state motion that's given by delta is equal to L by R plus KUS into U squared by R into G. So this is what we have seen. So in this, if delta is 2L by R, I would have my velocity, what is called V characteristic. So if I take delta F is 2L by R, that's equal to L by R plus KUS into U squared by RG. So I would have my U characteristic speed in this given by GL by KUS. So GL by KUS can also be written in terms of K3 as 1 by K3. So if I take stability factor and I write characteristic speed, it's simply 1 by K3, because you have just defined here the relationship between K3 and this. So GL by KUS is what is equal to K3. Right? GL by KUS is what is 1 by K3. So that's what has happened here, 1 by K3. So this is what is your characteristic speed. Characteristic speed. So you can also say with respect to, so that is this speed, that is this speed. Then if the vehicle parameters of the tire compliances in the front and rear in steady state motion is such that you have your understeer coefficient is negative. This is the case of the vehicle condition, and you would see that at that time you will have in denominator this sign is going to be minus. So though it is increasing trend like that, and it will increase very rapidly, what will happen when the value of KUS by G into U squared is same as that of L. So L minus, there's a time then denominator becomes 0. At that time, your yaw velocity gain reaches infinity. So then it would go like that asymptotically. So the value here, when it reaches, and that value is what is going to be referring to V critical speed. So V critical speed is the one we have seen that when delta becomes 0, right? If it is of oversteered vehicle, then delta equals 0 condition is what is going to be giving me this. So 0 equals L by R plus KUS into U squared by RG. So your KUS or U critical would be, this goes on this side, and then it would result in under root of GL by minus KUS. GL by minus KUS, or it can be simply written as 1 by K3. So minus K3. So stability factor would be minus in case of oversteered vehicle. Oversteered tendency vehicle. This would be understeered tendency vehicle. Or understeer vehicle, right? So what is that you are saying? What does that opt board? So if your vehicle here is of oversteered vehicle, the tendency of oversteered vehicle is very sensitive. The vehicle is very sensitive for the steering response. That's the meaning. So if I have my yaw velocity gain for oversteered vehicle, so this is for oversteered vehicle, it goes like that, where KUS is less than 0. Here it is of understeer tendency, where KUS is greater than 0, but we know, right? So, what do you mean by that? Oversteer vehicle is more sensitive for the steering input. That's the meaning of oversteer vehicle. Whereas understeer vehicle is more responsive for the least responsive for your steering input. So, if your vehicle is given a steering input and you say the vehicle is very sensitive to my input, that means that vehicle is oversteered vehicle. So, what do you mean by oversteer? Tendency is this: the result, this is a steering response point of view. The oversteer vehicle has the most sensitive handling characteristic. So what I mean by that, oversteer vehicle is most sensitive to the steering input, given steering input, or you can say most sensitive handling characteristics. And sensitive handling nature of the vehicle. So oversteered vehicle is most sensitive to the given steering input. Hence, it is called sensitive handling nature of the vehicle or behavior of the vehicle. Whereas on the other hand, when you say understeered vehicle, right, this is for oversteered vehicle. On the other hand, when an understeered vehicle, you would use the word least responsiveness of the vehicle, right? You would use the word is the least responsiveness of the vehicle, right? Understeer vehicle refer to least responsiveness or least responsiveness to the steering input. So what does that means? What does that means? Say I have my vehicle designed for an understeer tendency. I have my understeer coefficient positive. And if I go with the smaller speed and if I have to give my steering input for maneuvering, that's fine. We could correct it. If I have to go higher and higher speed, like you see here, around 150 kilometers per hour, the steering input needed to negotiate is become doubled what would happen when it is for a neutral steer vehicle, right? So it is L by R become 2L by R. So that become very sluggish. So the responsiveness become least responsiveness. So understeer tendency always refer to the least responsiveness of your steering input. Oversteer tendency would be always most sensitiveness of your vehicle. So the word of sensitiveness always go with oversteered vehicle. The responsiveness goes with the least responsiveness goes with an understeer vehicle. So neutral steer vehicle is what is on both sides. It is going to have a good responsiveness as well as a good sensitive for the steering input. That's why your vehicle is always designed very close to neutral steer and then slightly slight values of KUS. So you would have your characteristic speed would be much ahead than the requirement of steering, can be at ease achieved. So if your steering is not power steered vehicle, you see the world 10 years before or 15 years before the vehicle, which are not power steered vehicle, you just to see that how cumbersome it would be. So if you have to steer manually, you would see there are tremendous effort that you have to give when you have to negotiate cornering with the higher speeds. So that is what is the meaning of sluggishness or responsiveness, least responsiveness of an understeer vehicle. On the other hand, if the vehicle is oversteered, most sensitiveness of the vehicle would be realized as soon as your speed become a characteristic speed, which is smaller than that of your um, characteristic speed. Why? Because for a vehicle to behave as oversteer tendency vehicle, the steering input 0 is what is achieved. You don't require to steer at all later on. So when you don't give steering and then vehicle maneuvering is something very hard to imagine. And that is what is taking you the vehicle from controllable zone to an unstable zone, wherein yeah, the steering is not possible. Right, so this one to understand like this, there is another gain called curvature gain. I will go from here to this curvature gain. So that would say this unstable state very nicely. So let's just go to this, then come back to this lateral acceleration gain. Right. So how do I go and explain you now? The second gain is curvature gain. G kappa curvature. So it's kappa. So that's going to be 1 by r. Curvature is what? 1 by turning radius is what is defining curvature for the given steering input. And this would be obtained by this relationship. I know r into capital R is what is forward speed, kinematics, right? So where r is yaw velocity, capital R is turning radius. And when I do this product, I get what is called the forward speed. So if I have to get 1 by r, so 1 by r, that's nothing but r by u. So I have already here r by delta. So it is simply r by u delta, r by u delta. And it is, in this s tends to 0, whatever that I have is what is my gain. So already what I had is u by, so this is u by u into L plus KUS by G into U square. So this is what we had, right? So this U goes off. So I will have curvature gain given by 1 by L plus KUS U squared by G. So this is my curvature gain formula. So curvature gain again is function of wheelbase, function of understeer coefficient and forward speed, right? And forward speed. So now, how do I plot its variation? So that's what is very interesting. So what do you mean by curvature? See, let me just look at this, the path. So this path is what is say given by R. So when I say what is curvature of this is kappa is what is 1 by R. So the more the curvature means what? The less the radius. The more the radius means less the curvature. So my vehicle goes in this. I have my vehicle travels in this. So, during the given steering input, so that goes in a less curvature cut. That means this radius is more, 50 meters radius. So if the curvature is more, what would happen? So there's some noise. Please mute yourself. that would be really difficult for me. So please mute yourself in case you forgotten. So what is curvature now to look at? See here, if my turning radius reduces, that means this is my curvature. So now curvature increase is what is bringing my turning radius down. So this is for that. So like that, the smaller the curvature, the bigger the radius, the bigger the curvature, the very sharp turn is what is no, high curvature. In high curvature, it's turning radius somewhere here. So what would happen if I have this goes like that? When this curvature become infinity, then the radius becomes zero. So the kappa tends to infinity. That means the radius tends to zero. That's a condition. So when radius tends to zero means what? Radius tends to zero means what? The turning radius is zero. That is that's going to be coinciding with your CG of your vehicle, and then the vehicle instead of taking a turn would start spinning, and that is an unstable state of your vehicle. So that would happen when your vehicle reaches its critical speed and the vehicle understeer coefficient is negative, and the vehicle is an oversteered vehicle. So oversteered vehicle, when you drive in its steady state motion under the critical speed, you would see that vehicle instead of going in a controlled manner in a given curvature, it would get into infinity curvature, and R tends to zero and vehicle would start spinning uncontrollable it becomes. So that's what is that you could see from this tendency, from this gain. So to understand that, let's again plot this in this equation. So let me take vertical axis, my curvature gain, G curvature, and then horizontal axis, let me take speed of my vehicle. So this is 50, 100, 150 kilometers per hour. And you see my equation here. When KES is zero, that's neutral state condition. So that's 1 by L. So L is 3 meters for the chosen vehicle. So that's going to be constant. And that's 1 by L here, your gain for neutral state vehicle. That is KUS is zero. When KUS is zero, your gain value is just 1 by L. And that's this, right? What will happen if KES is positive? Your understeered vehicle, you will have here, this is positive. So the numerator is 1, denominator you have positive term here. So as you increase the speed of your vehicle, the denominator increases and curvature decreases. When curvature decreases, you would have your variation would be something like this. So the curvature will start decreasing like this. So if this is the way it decreases, and this is your KUS is greater than 0, referring to an understeer tendency of the vehicle. If KUS is negative on an oversteered vehicle, you see that 1 by L minus KUS U squared by G. So there is an increase at the beginning, and that would keep increasing, and there is a point when the denominator become the denominator value keep decreasing gradually and become 0. And as the denominator decreases, the gain value increases. So the gain value would increase like that, and it will reach to infinity when it is reaching to a critical speed. When it is reaching to critical speed. So this is oversteer tendency where KUS is less than 0 value, right? So this is how you would have your variation. So the moment the KU is approaching to less than 0, and your vehicle gain tending to infinity, that corresponds to critical. At U critical, you will have radius tends to 0. The turning radius 0 refer to spinning of your vehicle. Of vehicle. So that is referring to an unstable state. no control of steering that's possible. So the oversteered vehicle gives most sensitive behavior, but still, for a safety point of view, we have to take care of that. So that's what is physical interpretation of having a curvature gain of a different vehicle. I could be able to compare the class of vehicle for different steady state condition. So similarly, the third curvature is what is the lateral acceleration gain. So that's G lateral acceleration gain. So that's going to be obtained in terms of this. So how do I refer to? You can say that that's going to be lateral acceleration. So lateral acceleration is AY by delta as s tends to 0. So that's going to be Ay. Here is, since it is steady state motion, this Ay is given by u squared by r by delta. So u squared by r by delta, I can rewrite it as this way. So r is equal to u. So u by r is what is r is equal to u by capital R. So u by capital R is R. So it's R into u by delta. So R by delta is yaw velocity gain. I had to multiply that by u. So I know yaw velocity gain already u by L into 1 plus k3 u square. So that's going to be multiplied with u again. So that's going to be u squared by L into 1 plus k3 u square. Or in terms of KUS, right, it is going to be u squared by L plus KUS by G into u square. What is my yaw velocity gain? G, lateral acceleration gain, I can also represent my lateral acceleration gain in this way. So here, what is this? Is Ay by delta I have it, and Ay by G. I can represent my lateral acceleration in terms of G. So Ay by G when I take by delta is what is I define as this lateral acceleration normalized by G. Then this G has to be taken on this side that equation, right? Ay by delta. So I require this G. So when I divide this by this side, I have to divide by G denominator. So that's going to be u squared by G into L plus KUS into u square. So I can have this as the definition or the expression for lateral acceleration gain. So this lateral acceleration gain, you can plot as function of speed, and then we will stop today's class. So you have here Ay by G. See, divide by G, I have done it. So this is normalized by delta. So this is in my y-axis, and vehicle speed, forward speed in x-axis. So this is 50 kilometers per hour, 100 kilometers per hour, 150 kilometers per hour. And then I would have my neutral steer tendency. See here I have my expression u squared in numerator and denominator also. So when KUS is 0, you know that's neutral steer vehicle. So it's u squared by GL. So numerator I have u squared, which is parabolic variation. So my vehicle tendency would be something like this. That is of neutral steered vehicle when KUS equals 0. So the lateral acceleration gain would increase as my speed increases in this fashion. If it is of neutral steered vehicle. If it is of understeered vehicle, what will happen? This is going to be positive. So my value would keep increasing denominator. So this is going to be decreasing. So I would have initially it is like that, and then it will go like this. So this is what is I understeered vehicle with the KUS greater than 0. With the oversteer tendency, you see that this minus here. So at one point of time, the denominator would, what will happen as speed increases, denominator get decreases, and the gain value increases, but the denominator value becomes 0, that it shoots up to infinity. So this value would change it rapidly, and it will go to asymptotically meeting when velocity u critical is achieved. So this is oversteered vehicle. Oversteered vehicle when KUS is less than 0. So this is what is the variation it will be. So what you can do, these three equations that we had, you can use the Excel sheet or your MATLAB, define this function and vary, and you can plot this as a function of speed, and you see these characteristics plots, right? So if you choose a different vehicle, for example, same brand of vehicle, hatchback, sedan class or SUV vehicle, and vehicle parameters would decide this KES value. So if you take those values and you can compare three vehicle segments of a same brand, and you can compare, or like that, to do a comparative study. Such a steady state gain is quite useful, and that would help you to calculate what is your critical speed and so on in your functions are in your code that you are writing using these equations. So these are very simple, which are steady state gains to readily look at and comment on the vehicle handling nature. But when you want to design your vehicle and fine tune the nature, and you have to go in for designing your control strategies, control systems. When you have to design your control system, instead of looking at your steady state gains, you would look at your transfer function straight away, and those transfer function would be part of your mathematical model. So best example is in right model also you have looked at your transfer function. So the force transmissibility or displacement transmissibility is what was there. So you give your vehicle the input which is coming from road, and then your vehicle model described by your transfer function, and then you get your output, which is in power spectral density function of acceleration at the target location. So that's what you have seen. So any mathematical model would essentially will have the nature of your vehicle, and that would be dictated by its transfer function, and the specific safe motion, steady state motion. If you want to do a comparative study, these steady state gains are the ready metrics to do so. So with that note, I would stop today's lecture. And if you have any doubts, I would answer. Otherwise, we'll end the lecture. So I'll stop.